Welcome to our deep dive today. We're going to be exploring a novel approach to making virtual reality more inclusive.
Oh,
We're examining a research paper.
okay.
It's titled SoundHapticVR, Head-Based Spatial Haptic Feedback for Accessible Sounds in Virtual Reality for Deaf and Hard-of-Hearing Users.
Mm-hmm.
It focuses on enhancing the VR experience
Yeah.
for individuals who are deaf or hard of hearing.
Mm-hmm.
And get this,
Okay.
the researchers
Yeah.
use vibrations on the head to represent sounds
Interesting.
instead of relying on visual cues.
That's a significant distinction.
Yeah.
This research aims to deliver a more holistic and immersive experience by translating audio cues into tactile sensations.
The paper stresses how critical sound is for a genuinely immersive VR experience.
Right.
It's vital for spatial awareness and conveying information.
Think about a VR game where you need to hear an enemy approaching from behind,
Oh, yeah.
or a virtual environment where sound guides you to a location.
Right.
DHH users often miss out on these essential cues.
And the paper highlights how current solutions,
Like what?
subtitles, icons, mini-maps,
Yeah.
they can clutter the visual field and don't fully replicate the immersion of sound.
It's a compromise.
Yeah.
While they attempt to provide information, they also risk sacrificing the visual clarity and engagement that VR is known for.
This research team chose to explore a different path. They created SoundHapticVR.
What is that?
It's a wearable device
Uh-huh.
that attaches to a VR headset
Okay.
and converts audio signals
Yeah.
into localized vibrations on the user's head.
So the device uses multiple vibrotactile actuators
Right.
to create a nuanced and spatially accurate haptic experience.
So it's not just a single vibration.
No.
It's a carefully designed pattern
That's right.
of vibration
Yes.
that represents the direction and type of sound.
You can actually see a picture of the prototype in the paper.
Oh, wow.
It's attached to the head strap of a standard VR headset. It has a streamlined design. One of the first challenges for the researchers
Was figuring out the optimal placement for these actuators. Where on the head are we most sensitive to vibrations?
Right.
How does that sensitivity affect our ability to perceive the direction of sound?
That's a good question.
They did a preliminary study
Uh-huh.
with 12 DHH participants,
Okay.
testing the maximum perceivable vibration frequency on different head regions.
Yeah.
They learned that sensitivity varies across different areas. They even found that the back of the head was the least sensitive
Why?
hair thickness. This finding played a crucial role in deciding where to place the actuators for maximum effect.
It's surprising
Yeah.
that the forehead was the most sensitive area.
That makes sense when you think about it.
How so?
The concentration of nerve endings in that area,
Yeah.
the forehead is very sensitive to touch, generally,
Yeah.
making it a prime location for receiving this type of haptic feedback.
This leads us to the next phase of their research,
Which is?
testing different actuator setups to determine the most effective one for sound localization. It's a captivating challenge from a design perspective.
Yeah.
They had to consider not only the number of actuators,
Okay.
but also their precise placement, a system that accurately conveys spatial information.
In study 1, they tested 4 different configurations,
Okay.
each with a different number and placement of actuators.
Makes sense.
The goal was to figure out which configuration enabled DHH participants to most accurately locate a virtual sound source using only vibrations.
So they created a meticulously controlled VR environment where participants relied solely on haptic feedback to pinpoint the source of the sound,
Was ensured,
that their responses were based purely on tactile information.
eliminating any visual cues.
Precisely. The results of the study were quite unexpected.
In what way?
A front-facing actuator significantly enhanced accuracy. Having that additional reference point proved to be very helpful in allowing participants to triangulate the sound source.
So more actuators is better.
Well, not always. The configuration with 4 actuators,
Okay.
while seemingly more comprehensive, resulted in sensory overload.
Too much information.
The constant vibrations from multiple points on the head hindered localization rather than improving it.
Interesting. So what was the best?
The most effective setup turned out to be left, right, and front, or LRF as they called it.
LRF.
Yes. This particular configuration struck a balance between providing sufficient spatial information for accurate localization and avoiding the discomfort of excessive sensory input.
But that's just the beginning.
Right.
Now we know the optimal configuration.
Yes.
The next question is, can this setup convey different types of sound?
That's a good question.
And that's what Study 2 set out to investigate.
This was an important next step.
How so?
Because the ultimate objective is to design a system that doesn't just provide directional information, but also contextual information about the sound itself.
Sure.
Can we distinguish between a dog barking and a car horn? Using only vibrations on our head, that was the question they sought to answer.
How did they test that?
They used a different VR environment.
What was it?
A child's playroom.
Okay.
Filled with objects making various sounds. Participants had to locate these objects based on a text description and the feel of the sound.
I see.
The choice of a playroom environment was quite clever.
Why is that?
It's a familiar setting with everyday sounds that people can relate to. It also allowed for testing the system's efficacy with simultaneous sounds.
So more like real life.
Exactly. And some sounds were much easier to identify than others.
Give me an example.
Participants achieved 100% accuracy in locating the waterfall sound.
What do you think that was?
The consistent and strong vibration pattern of the waterfall sound made it easy to pinpoint. One participant even said it felt as if they were standing next to an actual waterfall.
Really?
The gunshot sound was another one that stood out.
How so?
With 96.67% accuracy, its distinctive pattern made it easy to recognize.
So the pattern itself is very important.
Very much so. Sounds with clear, distinct patterns are considerably easier to identify through tactile feedback than sounds that are more subtle or have overlapping frequencies.
But not all sounds are that easy.
True. Some sounds, particularly those that were similar, proved more difficult to differentiate.
Such as?
The car horn and dog bark, for example. Their vibration patterns were similar enough to cause confusion, especially when the objects making those sounds were close together in the virtual environment. It seems that even with this innovative approach, there are still challenges in representing complex soundscapes through haptics.
That's true, but being able to distinguish even some sounds in this manner is quite remarkable.
It is.
It opens up exciting possibilities for making VR more accessible.
Definitely.
And for discovering new ways to interact with virtual environments.
After all this experimentation, the LRS configuration emerged as the most effective and comfortable setup. And importantly, the research demonstrated that DHH individuals can successfully locate and identify at least some sound sources using vibrations on their head.
I find the fact that familiar patterns are easier to recognize.
Yes.
Particularly promising.
This hints at the potential for personalization. Imagine a system where you can tailor the vibration patterns to your own preferences and experiences. This would make the system even more intuitive and user-friendly.
This research has major implications for improving the accessibility of VR for DHH users.
Consider VR games, navigation apps, and other sound-based experiences designed with this technology in mind. It could open up a world of possibilities for individuals who have historically been excluded from these experiences.
There's obviously much more to explore and refine.
Of course.
But this research is a significant advancement in making VR a more inclusive and immersive experience for everyone.
I agree. And it highlights a broader trend in accessibility research, moving beyond replicating existing experiences and exploring novel ways of interacting with information and technology.
That's an important observation. It's not just about equality, but about expanding the range of possibility.
Right.
And creating experiences that are enriching and engaging.
Yes.
For all individuals.
Exactly.
Regardless of ability.
Yeah.
What's fascinating is that this research could have implications that go beyond accessibility.
Oh, how so?
Imagine if we can convey sound information through touch. What other sensory experiences could be translated in similar ways?
You're giving me something to think about. Could this be applied to other fields?
Sure.
Perhaps to help people with visual impairments experience virtual environments in new ways.
Exactly. Or consider applications in gaming or entertainment where tactile feedback could create another layer of immersion, even for users without disabilities. This research has gotten me thinking about the future of sensory experiences.
Me too.
And how technology can blur the lines between the physical and virtual worlds.
Bringing this back to the big picture.
Yes.
It points to a shift in how we think about accessibility. It's not just about accommodations or workarounds,
Right.
but about using technology to build a more inclusive and multisensory world for everyone. This deep dive has been pretty insightful. Let's recap some of the main points from the research.
Okay.
First, they built this innovative SoundHapticVR device that turns audio signals into vibrations on the user's head.
And then they carefully tested and refined it
Yeah.
to figure out that the LRF configuration with actuators on the left, right, in front of the head was the most accurate and comfortable for localizing sound.
And then they took it further.
Yes.
And asked if this configuration could convey different types of sounds.
Not just direction.
Exactly.
The sounds themselves.
And what did they find? That certain sounds.
Yeah.
Like the waterfall and the gunshot were easy to recognize just from their vibration pattern.
It's like they created a whole new language.
Yes.
A tactile language of sound.
Exactly. It's about developing a set of patterns that the brain can learn, just as we learn to connect sounds with their meanings.
But there are still obstacles. Telling similar sounds apart remains difficult.
Yeah.
Especially when those sounds are close to each other in the virtual world.
As the researchers said, this is only the start. More research is needed to explore the full potential of this technology and to work on these limitations.
But this research paints an encouraging picture.
It does.
Of what VR could be.
Yes.
A future where sound isn't a barrier to taking part.
Right.
But a chance for greater immersion and accessibility.
I agree.
Now, I know we have more to discuss the next part of this deep dive.
I do.
So I'm curious, what has stood out to you most from what we've talked about so far?
The idea of using the body as a surface for sensory information is fascinating to me. We tend to think of our senses as separate things, but this research shows how we could design cross-sensory experiences. Experiences where touch can augment or even stand in for other senses.
It makes you think about the possibilities of combining this haptic technology with other sensory inputs. Could you incorporate things like temperature variations or subtle air currents to create richer, more nuanced experiences?
It's a really intriguing idea. Imagine a virtual reality environment, and you can not only feel the rumble of an earthquake through vibrations, but also feel the temperature shift as you got close to a virtual fire.
That would be amazing. It would bring a whole new dimension to virtual experiences.
Yeah.
It would make them even more immersive and more true to life. And this brings us back to that thought-provoking question from the researchers. What other sensory experiences could be translated into tactile feedback to improve accessibility and create truly immersive experiences for everyone?
It's a question with so many possibilities. As technology improves, we might find ourselves interacting with virtual worlds in ways we can't even imagine right now.
Yeah.
The great thing about this research is that it addresses a specific need for accessibility, but it also opens up all these new possibilities. Possibilities for sensory design and human-computer interaction.
It reminds us that the best solutions often come from thinking outside the box.
Yes.
And from challenging our assumptions about how we experience the world.
And it's about embracing the diversity of human abilities. Recognizing that technology can help break down barriers, it can help create a world that is more inclusive and engaging for everyone.
This deep dive has given us a lot to think about. From the clever design of the SoundHapticVR device to the bigger picture of what this means for accessibility and sensory experiences in the future. Thank you for joining us on this journey. We can't wait to see where this technology goes and how it will change the way we interact with virtual reality and the world beyond.